Alright, today I want to look at a seedy story of maths, murder and deception. I'm titling this story Underbelly, Surds. We're going to look at the leader of a secret society, the Pythagorean Brotherhood. Pythagoras, of course, was their leader. Pythagoras believed that all the real numbers, he believed in a perfect order. He believed that all the real numbers were rational. And as you know earlier, rational numbers can be expressed as a fraction a over b. And his brotherhood believed this as well, that every number could be expressed in this form, a over b. So as a decimal, they would either terminate or repeat. One day they were out on their boat, and one of his members, Hippasus, suggested that when you took a square of unit length, so 1, 1, 1 and 1, and you calculated the length of the diagonal, which using Pythagoras' theorem, c squared equals a squared plus b squared, this being c, 1 squared plus 1 squared, c squared equals 2, c equals the square root of 2. Hippasus suggested that the square root of 2 was in fact irrational. It could not be expressed as a fraction in the form a over b. It was not rational. And not only did he suggest this, he said, in fact, I can prove it. Now, being the leader of a secret society that doesn't believe this sort of thing, Pythagoras did the only reasonable thing, and being out in a boat, he took Hippasus and threw him overboard and drowned him there in the ocean, so that his secret would die with him. So this was a bit of a shattering of Pythagoras' world view, and in fact we now know that Hippasus was in fact correct. Well, some people would say the story is just an urban legend, and that aside from rational numbers, real numbers also encompass another set of numbers, and they're these irrational ones. They're not rational, they're irrational. Some people would say that's absurd. But with irrational numbers, there are a set of irrational numbers, and there's different types. We've already met some. We've met pi. We know pi. There's another one. There's another one called e that you'll meet later on in your studies. I think it's 728, I think. That might be wrong. Check that one out. And then, of course, as well, there's the square root of 2, as Hippasus suggested, 1.4, and so on. Now, he suggested he had a proof for this, and I'll make another little video showing you a possible proof. But for now, we just want to focus in on, out of these irrational numbers, we want to focus in on ones that can be expressed in this format. And the ones that can be expressed as the square root we'll call surds. And our surds, and in some texts, they may be called radicals. In fact, when I taught in Canada, that's exactly what we called them, radicals. So surds or radicals, and so they're the numbers of the form like this: the square root of 2, the square root of 3. I'm not going to include the square root of 4, you can work out why. The square root of 5, the square root of 6, the square root of 7, the square root of 8, and again I'm skipping the square root of 9, I'm jumping to the square root of 10. So surds are written in this form. Now, aside from their history of murder and deceit, these irrational numbers, and surds in particular, are fascinating numbers. And what they've done is they've really expanded. They took this little narrow world view of real numbers and expanded it into a whole lot of extra numbers, which is pretty awesome. Now, there's some pretty cool numbers that come out of this, and so if we're thinking about mathematics, I know a lot of you probably think mathematics has to be something that is used and nothing else, but I see mathematics as a bit of a creative endeavour and something that's really exciting and unique. And so one of the best things about surds, I think, is some of the cool numbers we get. And one of those cool numbers would be a number called phi. And so that can be found by taking this expression with a surd in it, 1 plus the square root of 5 over 2. Now, if you do that, you can get a decimal approximation for that, of course. It will only be a decimal approximation. Just plug it in your calculator, and you should get something like this happening. And it will, in fact, be irrational, which means as a decimal, it will neither terminate nor repeat. It will go on forever as a decimal. Alright, now what's really cool about this number, and I want you to check this out, and we can use this as our proof of homework. I want you to take this number, put it in your calculator. Oops, that's a 5, not a 2. And then I want you to square it. And I want you to write down the decimal approximation when you square it. And then what I want you to do is I want you to find its reciprocal. So I want you to find 1 over this number. I'll let you work out how you'll do that on your calculator. I want you to find the reciprocal, and I want you to write down the decimal approximation for that. And see what sort of cool results you get when you look at the decimal approximation. Very funky number, and if you want to know more about that number, I want to look at the golden ratio. One of those numbers that just pops up every now and then in amazing little places. So have a look at the golden ratio. So proof of homework, jot that down, and I'll let you know. And then you can add it to the web page comments section. Now, one of the cool things about surds is whilst as a decimal they never terminate or repeat, they go on forever, we can in fact locate them on a number line. And the way we do it is like this. So we have our number line, 0, 1, 2, 3, 4, spaced out. What I've done is I've just drawn a second line that is also 1 unit away. So, well, that's 1, that height there is 1. And then I'm going to use Pythagoras' theorem, which I think is a bit ironic considering our original story said he disagreed with these numbers. Oops, a bit hard to do with one hand. There you go, drawing the triangle. And we've already calculated this one earlier. We said when it's 1 and 1, this is the square root of 2 up here. And so what I can then do to find out where that square root of 2 lies on this number line, I can take a compass and open up this wide, the square root of 2 wide, and draw the arc. And where it crosses that number line, which you can't see because my hand's in the way, where that arc crosses the number line there, that point there will be the square root of 2. So I've effectively placed the square root of 2 on the number line. Now I can actually do this for the square root of 3 as well. Having placed the square root of 2, I'm going to draw a perpendicular line up here. A bit hard with one hand, as I said. I'm now going to create a right angle triangle. And the base of this right angle triangle is the square root of 2 long, and the height is still 1. So to get Pythagoras' theorem, I'll go c squared is equal to a squared plus b squared. C squared is equal to the square root of 2 all squared plus 1 squared being the two sides. That's 2 plus 1 is 3, so c squared is equal to 3, so c must be equal to the square root of 3. So in other words, this length along here now, from 0 up to here, is the square root of 3. And so once again, just draw my arc down, and where that arc comes in here and crosses will be the square root of 3. And so on. Okay, so that's how we put surds on a number line. Now if I continue that process and do it again one more time, which number will I arrive at next?